Hello, and welcome to What's New in Griddle 3.0 webinar. My name is Andrei Petigorits. I'm a senior engineer in ITASCA consulting group, and I'm also Griddle product manager. Let me start this presentation with a general description and brief reminder about what Rhino is and how Griddle operates with it. Rhino is a CAD software and a free-form surface modeler. It is heavily used for computer-aided design and computer-aided manufacturing, in architecture, industrial design, engineering, graphics design, and so on. Here you can see some images of Rhino interface with some design shapes. On the left side, it's actually various polysurfaces and curves representing, let's say, this car and teapot. And on the right side, you can see meshes. So this gives you an idea of what Rhino works, what kind of objects Rhino works with, and what can be done in Rhino. But a bit broader list of these objects is presented here. And among these objects, we're actually interested in particularly two types of objects, which are polysurfaces represented by boundary representation or BREP. This is an analytic type of object, and this is some other analytic types of objects that also present in Rhino. And we're also interested in surface meshes, which are discrete type of objects. And there are collections of vertices, edges, and faces with known connectivity between them. Any type of analytic object can be triangulated to produce surface meshes. And then we can work with surface meshes to create volume meshes. And from volume meshes, we basically can export them to numerical models and use them for numerical modeling. So that's where Griddle comes into play. Griddle is a general purpose meshing plugin for Rhino. Even though Rhino itself has pretty extensive capabilities to work with meshes, those meshes or those capabilities are designed mostly for, let's say, design, architecture, and manufacturing. However, if we want to create volume meshes for numerical modeling, Rhino comes a little bit short in this area. So Griddle fills this gap. It utilizes and extends Rhino capabilities related to meshing. When users install Griddle, this Griddle toolbar will appear in Rhino interface, and it contains number of icons. Each icon, when you click on an icon, a command gonna be issued, and some specific operation will be executed in Rhino. Griddle 3.0 is currently compatible with Rhino 8 only. In future, we will extend its compatibility with later versions or newer versions of Rhino, but it's not compatible with Rhino 6 or 7 due to some technical reasons, mostly coming from Rhino side. Griddle includes tools for structured meshing. This is this tool in this container. It's Block Ranger. Tools for unstructured mesh and these three tools, and tools for editing and manipulating surface meshes. This collection of tools here. Griddle can generate meshes or grids for ITASCA software like FLAG3D or FreeDeck, and also some finite element codes like Abacus, ANSYS, LSDyna, and Nastran. And that also can provide VTK output. Here you can see how typical mesh output would look like if unstructured mesh is generated by Griddle's unstructured mesher, and a variety of information will be provided on in the layers panel as shown here. We will talk about this on the future slides when we talk about GVOL improvements. So here's the outline of the presentation, overall outline. We will cover a variety of tools and variety of improvements here. So major improvements have been done in pretty much all the tools except maybe a couple of them. And we also introduced new tool, gCollapse. We'll talk extensively about it. And we will briefly touch on smaller changes and improvements that were done in gsurf and Block Ranger. So let's start with unstructured meshing tools. And I'm gonna go directly to gint. Gint is a surface mesh intersector. This is a very important tool for us because it provides conformal intersections between meshes. So on the input, users can choose or select a number of non-conformal, non-properly intersected meshes, then run surface mesh intersector and create conformal or proper intersections between the meshes. And this is important because unstructured volume measure GVOL requires input surface meshes to be fully conformal. Otherwise, it's not able to create volume elements around non-conformal meshes. So this tool is necessary to use to create volume meshes. However, previously, it was a little bit hard to figure out what kind of tolerance to use in surface mesh intersector. Meshes can be touching each other, can be not touching each other, can be intersecting, and tolerance value was not always easy to figure out. However, now GINT, we rewrote GINT, so it is a two-step intersector. On the first step, it only detects and highlights intersections as shown here. You can see that this cylinder is not fully intersecting the box. As we can see, highlighted intersections are kind of broken, but when we adjust tolerance, we can make full intersection between cylinder and the box. So knowing that we got full intersections here, we can use this tolerance to actually proceed with intersecting and modifying the meshes. Intersected faces can keep the highlight after the operations are done, as shown here, and they can also be split from the original meshes to do maybe some specific operations just with intersected faces. GINT also provides the ability to choose how to intersect selected meshes. For example, intersect only distinct meshes, or intersect meshes within themselves, or self-intersect, or do both. By default, it is a full intersection, meaning that both of these operations or both of these options will be accounted. GINT, another important feature is that GINT does not convert non-intersecting quad faces into triangles and preserves all non-intersecting parts. This can be seen here. You can see that all the quads that were not initially intersected, they are preserved in the final mesh. Griddle 10 and 20 used to triangulate all input meshes that were selected for intersection. And that sometimes created difficulties with future operations. Finally, we introduced more automatic checks for possible mesh issues before doing intersections, so GINT is more robust now. With this, let me show actual example of GINT use, and I'm going to switch to Rhino. All right, let's take a little bit deeper look at GINT, and here's the model I'd like to show. It's a model of a large dam with construction stages shown in red and blue, and this is not a complete model. You can see that there's no domain present, but it's enough for us to see how GINT operates. None of these meshes are conformal, meaning that faces don't match along possible intersections. So GINT is necessary to intersect all these meshes to make them conformal for possible remeshing afterwards and volume meshing. So let's select everything with Control A and then click on GINT icon. Initial intersection detection logic works, and it highlights possible intersections with these yellow highlights that corresponds to this zero tolerance. However, none of the intersections have been done yet. Meshes have not been modified. It's only the highlight that's shown right now. We can see that there are no full intersections or complete intersections because these regions are kind of broken. So let's try to increase the tolerance. Let's use this value. And we see that we still don't get full intersection because these regions are not complete. Let's increase it one more time to a pretty high value of 0.1. And now we see that there are pretty much all the possible or visible intersections are highlighted, meaning that this might be good tolerance. So we're going to use it to intersect the meshes. One thing I'm going to do here, I'm going to go to advanced parameters and click on show intersections to highlight all the intersected faces after the operation completes. You can also read in GINT documentation, which you can invoke by pressing F1 button or going into Rhino embedded help about all other options. Also, I would like to note that there's preview limit. If you set this value to 0, GINT will not highlight intersections when you click on it. However, it doesn't mean that the operation will not work. It will work just as before, it's just highlights not going to be shown. And this is done to speed up geint operations on very large meshes. For now, I'm just going to press enter for geint to actually proceed with intersections and modify meshes as needed. We can see that all intersections got highlighted with its red outlines, and these red outlines are non-interactive. It's delegated in the new layer that was created, and it's called mesh intersections. You can delete this layer, hide or show it, maybe change colors of this highlight, but otherwise these highlights are not interactive. And we can also notice that none of other mesh faces got changed, only the intersections appeared and faces locally were modified. So this is geint, and now let's switch to another Griddle functionality. We're back at the presentation, and let's briefly talk about gsurf, which is unstructured surface remesher. Remesher got new option, which allows remeshing input meshes in a way how Griddle 1.0 used to remesh them. So this option is specifically for people who like to use Griddle 1.0 or got used to use it. There was a change in remeshing logic between 1.0 and 2.0 version, and in certain cases, very specific cases, I would say, Griddle 2.0 produced slightly poor results than Griddle 1.0. So now Griddle 3.0 provides both options for users. Here's an example of such specific case. It's an example when element size is prescribed on number of meshes that connect to each other. And if people use default remeshing parameters in Griddle 2.0, they would get this type of result. But if they use new option in Griddle 3.0, they can get this type of result. This is kind of unique way of remeshing, and this nice type of results can be achieved in other ways by specifying minimum and maximum edge size, proper gradation, and some other parameters. So there's really no necessity to kind of roll back to using this approach, but for those people who like to use it, there's the option for you. Another thing that gsurf provides, it's more fixes in some specific cases where a remeshing engine could potentially fail. So now it's improved, and it improves element quality as well, and it is more stable on complex geometries. Also, remeshing speed is improved due to multi-threading, which is quite noticeable on large models. This is all about gsurf, and let's switch to the next item. Let's talk about unstructured volume measure gwall, which received significant amount of improvements in new version of Griddle. The first big improvement is that gwall now visualizes generated volume meshes, practically of any size, directly in Rhino. And on this image, you can see how this visualization may appear for an example model. gwall also can visualize poor quality elements with automatic filtering into bins based on element quality. They also appear here in red, and information about them is provided on the right hand side here. So corresponding layers are created for each of these bins, same for poor elements and element groups. And we will see that on actual example in a minute. gwall assigns element groups in a consistent and repeatable order based on subdomain volumes. You can see that volumes are listed here on the right side. gwall can now also include hard nodes and hard edges into the volume mesh and account for local element size assigned to hard nodes and hard edges. So I will show an example for that in a minute. Also, gwall runs extensive error analysis before proceeding with volume meshing. And for example, here you can see that a couple unenforced faces have been found. This is actually after volume meshing, but if there are issues before volume meshing, errors and issues will be reported here. And not all of them prevent gwall from running. As you can see, in this case, issues didn't prevent gwall from running, but in some other cases, gwall may not be able to continue running and errors will be reported. So this is this point. gwall also can generate surface groups for ANSYS, Abaqus, and LS Dyna now. Previously, it didn't generate surface groups. However, surface groups are generated via nodes, not via actual surfaces. So it's a little bit more simplified approach, but it's very robust. Also, Jewel can produce VTK output if needed. And there are some improvements related to FLAG3D and FreeDEC, mostly related to group assignment, specifically to surface meshes. For example, if surface meshes didn't have a name in Rhino model, there's an option to exclude them from FLAG3D model. This helps when users work with very large models containing, let's say, hundreds of surface meshes, and not all of them are relevant for numerical analysis. So there's no need to create a group name for them, and this simplifies identification of surfaces in FLAG3D. Also, users now can specify zone and phase slots in FLAG3D and FreeDEC, and they can Jewel also excludes some specific prefixes that were always there in previous versions of Griddle for surface meshes. And this happens when group names are provided for surfaces. So all these improvements help work with volume meshes in FLAG3D and FreeDEC and simplify operations with those meshes or grids. And now we're going to switch to Rhino and we'll look at a couple Jewel functionalities in more details. To illustrate how hard nodes and hard edges are taken into account by volume measure Jewel, let's look at this simple example. Here we have a very simple box-like mesh containing 4 nodes inside of it, or 4 points. So if we create volume mesh by selecting all of these objects, we can select, going into advanced options, select include to hard nodes or hard edges. So we will select yes here. Then using all default parameters, that's the mesh that got generated. Let me just hide the original model. So we can see that the vertices of generated volume mesh are exactly matching the initial hard nodes that were selected. And by the way, this point in the middle, it's an artificial point. It's the centroid of generated volume mesh. It's there only to indicate or to be used with the volume mesh. And the reason for that is because volume mesh is non-interactive, same as with gint. I cannot select it. See, I can only select actual objects here. But this is done because when generating volume meshes for very large models containing, let's say, millions and tens of millions of elements, the displaying and rendering real objects in Rhino viewports requires huge resources and may take significant amount of time. So having these non-interactive objects is much faster, much more lightweight. But because of that, we cannot, let's say, zoom in, zoom out to those objects. So using the centroids allows us to zoom in, zoom out and locate where the centroids of volume domains are. So this is basically volume mesh with hard nodes. Let's do the same with hard edges. So now we have the same model and we have one hard edge for which we specified such discretization that there will be 4 segments. The length of the edge is 40 and we specified discretization of 10 meters. So we will get 4 segments. So now if we select both of these objects and make sure that we're going to generate hard nodes, include hard nodes and edges, that's the result of the volume mesh that we got. Again, if I hide it, we can see that additional elements got generated in the center because there are 4 segments in the edge, 1, 2, 3, 4. One other important thing to note about volume mesh is that because it is non-interactive, it is actually not saved with Rhino model. So next time, if I save and open this model, all objects will be there, but the volume mesh will not show up. because it's only for visualization purposes and it's not saved with the model. So another example that I wanted to show, it's an example, a bit more complex example. I already ran it, and it shows a model of roadway and some bridge, or let's say some other roadway support here. So all the mesh is already conformal and properly remeshed, and I just wanted to show how the volume meshes look like here. So I already created volume meshes. Let me hide few objects here. And we can see that, for example, bottom volume mesh looks like this. We can see that in many places we get hexahedrons. And for example, this is how the volume mesh looks for the bridge support. We don't get pure hexahedrons because surface meshes don't match on both sides. But important thing I wanted to note here is information about poor quality elements. Very important to pay attention to poor quality elements with lowest quality. We don't get those here because it's overall pretty decent mesh, even though we got some average quality elements. But when we look at where they clustered, we can see that there are quite a few elements here. Let me actually hide element groups. And now we can see clearer what causes these elements to cluster here. And you can see they all pretty flat. So this reason for that is because input geometries form very thin wedges here. And this is type of geometries that typically cause poor quality elements. So by improving input geometries, we can improve overall volume mesh. So this is an example of how you can use information about element quality to analyze your model and improve your surface meshes to create better volume mesh. All right, now let's talk about tools for operations with surface meshes. And let me start with a completely new tool in Griddle 3.0. This tool is called gCollapse. This is a new tool that allows resolving overlapping or nearly overlapping meshes by collapsing parts of one mesh onto others if these parts are located within the user-specified distance. So quite often we receive and work with meshes that are obtained from geological surveys and some field data, and maybe some meshes designed in CAD software, and quite often mesh parts, different mesh parts may overlap. So it's really hard to build proper volume domains in these overlapping parts. So gCollapse can help resolving such overlapping cases. Here's an example of how gCollapse works. Let's say we have two simple meshes that nearly overlap in this central part. After gCollapse operation, some mesh faces of this yellow target mesh are deleted, and this mesh is extended towards base mesh. gCollapse has an option to automatically intersect the collapsed mesh with base meshes by using automatically calculated most optimal tolerance. It searches for that tolerance automatically and then uses it. So what's left after that is just remeshing, which simplifies operations with these complex meshes. gCollapse can also split collapsed meshes into parts located on different sides, opposite sides of base mesh, but it only works when one base mesh is used. And gCollapse allows controlling which collapsed mesh parts discard or preserve based on area parameter, because after collapsing, some mesh parts can be very small and they may be discarded as they may not be relevant for future work. Also, gCollapse allows using multiple base meshes. It automatically takes the union and then uses proper nearest surface towards two collapsed faces. The only important criterion is that multiple base meshes should be conformal between each other for proper operations. With this, let me switch to Rhino and show you actual example of using gCollapse. Here's an actual example that we're going to use to demonstrate how gCollapse works. Here we got model of open pit mine with 3 excavation stages. The data for this model were obtained from field surveillance, and you see the size of the model is pretty large, 1.6 kilometers. And we got 3 excavation stages. Stage 1, the shallowest one, then intermediate, green mesh, and the deepest stage 3, red mesh. So first, let's work with the stage 2 and stage 3. The reason is because stage 1 doesn't overlap in the center region with stage 3. So we first can take care of these 2 meshes. So let's collapse the green mesh onto the red one using distance 5 meters, which is pretty small in comparison to the overall model size, and it's on par with the element size. So I'm gonna use red mesh as the base, and collapsing G-collapse is working right now. First it removed nearly overlapping faces, then extended boundaries, and now it's searching for most optimal tolerance. So it completed the collapse operation, and we see that the meshes got cleaned up. The green mesh kind of got the boundaries got extended in normal direction to the red mesh, and grid mesh got split in 2 pieces. Let's actually separate them using split disjoin mesh command, because we are not interested in this little top piece. And now we have only 2 pieces left. It's very important to remesh after G-collapse, because we did aromatic intersection, and aromatic intersection quite often produces very thin, sometimes even sliver-like faces. So let's remesh these 2 meshes using these parameters to kind of replicate the original mesh element size. So this will clean up meshes after initial G-collapse, and will allow us to use this base mesh again for next collapse stage. So now if we show the stage 1, let me select actually stage 2, you can see that, let me go to top views, you can see that stage 1 doesn't really overlap with stage 2. That means we don't even need to consider stage 2 when collapsing stage 1 on stage 3. So we can simply take blue mesh and collapse it onto the red mesh. And we'll use the same parameters. G-collapse works again. It will automatically intersect these 2 meshes, and at the end we'll just check number of total intersections. Let's use mesh intersect command, and we got 2 full intersections as expected. This way basically we separated overlapping meshes, and you see that now it's clean topography, and we can easily create closed volume domains in between the excavation stages of this mine, and maybe closed volume domain above and below. So this demonstrates how G-collapse works, and now let's switch to the next topic. All right, we're back at the presentation, and now let's talk about G-heal, which is comprised of tools for fixing surface mesh issues. G-heal in Griddle 3.0 received some significant improvements, and we'll first start with the functionality show errors. First, there is a new functionality or logic to identify and fix n-gons in surface meshes. With Rhino 8 and possibly newer versions, many native Rhino operations lead to the creation of n-gons, which are mesh faces with more than 4 sides. This is a more general description or representation of mesh faces, which do not need to be limited only to triangles and quadrilaterals. However, n-gons are not suitable for volume meshing and other meshing operations, specifically for a type of volume meshes that G-Vol creates. So these n-gons have to be identified and fixed, and G-heal now does it. Also, G-heal now identifies duplicate faces that may sometimes appear when importing other geometry formats like DXF, and G-heal will report if there are duplicate faces present, and it can fix them automatically. And also we are significantly reorganized the output from show errors functionality, and now you can see over here that G-heal output is combined in one layer with sublayers reporting naked edges, clashing faces, n-gons, duplicate faces, and their amount. So this is just more intuitive and facilitates more efficient fixing process. Improvements in automatic heal include, as I mentioned already, triangulation of n-gons, removing duplicate faces, fixing clashing faces. This functionality has been significantly improved. Previously, we relied on Rhino functionality for this, which quite often incorrectly reported clashing faces, but now we use very robust mesh intersection engine and logic to identify nearly intersecting or self-intersecting faces in the meshes, and this allows fixing overlapping, intersecting, folding faces, so-called Z-folds, non-conformal faces, sliver faces and holes, and faces smaller than model tolerance. So we basically significantly broaden the number of issues that can be fixed with this functionality. We also introduced new functionality, remove non-manifolds, which removes small non-manifold mesh pieces, and it can be more than one face, it can be multiple faces, but it's quite useful in many cases. And finally, we significantly improved fill holes functionality, so now it's more robust and works for more complex geometries. With this, let me actually show you an example of G-Heal, and let's switch back to Rhino. All right, here's an example that I would like to use to illustrate G-Heal operation, and here we got a couple meshes. This is drift excavation or drift mining, and topographic surface. These meshes were originally obtained from field data, so they're actually quite broken, even though it's not readily visible. But first, I would like to show what would happen if we try to trim those meshes. Let's say this is our domain, and I would like to trim away these pieces that stick out from the domain. So let me select the interior meshes, and I use mesh split command. There are different ways how to trim pieces, but we'll use mesh stick just to illustrate that there's an option to create n-gons. So by default, splitting meshes will create n-gons. You can set this option to no, then all the intersecting faces will be triangulated. It's also not always good thing for future operations. But for now, let me concentrate on what n-gons are. So let me delete these extra pieces, hide box, and let's look what we got here by calling G-Heal show errors. You see that we got a lot of n-gons on the trimmed boundaries. We also have some holes. We got some duplicated faces, some non-manifold faces here, and actually over here as well. We can zoom in and see what's happening here. There's also non-manifold faces here, probably more than one, and another n-gon. And there's a lot of problems with the drift itself. So this is relatively small model, and we can fix all issues automatically at once. However, for large models, I highly recommend to fix issues discretely. Maybe if you expect to have holes in the model, first fix a hole. Then if you have non-manifold faces, fix non-manifold faces, and so on. But here, let's just run G-Heal in automatic heal mode. We will select all options, use default parameters or advanced parameters. You can read about them in the help. And let's just press enter. And we see that G-Heal automatically fixes all the errors here, which is great. We only have naked edges reported on the boundaries of the model, which is correct thing. So now let's just remesh this model using these default parameters that I preset. And we see that we got pretty nice mesh on the output. So after this, we can create closed volume domain by, let's say, extruding this mesh, maybe intersecting one more time, remeshing and creating volume mesh. So overall, this example illustrates how you can use G-Heal to fix various issues. And with this, let me switch to the next topic. All right, let's talk now about next tool, G-Extract, which comprised of tools for extracting mesh faces. We added several new tools or options here. The first one is extract within distance. By the name, you probably figure out that it's a tool for extracting surface mesh faces within user-specified distance from various objects. And these objects could be points, point clouds, curves and polycurves, surfaces and polysurfaces, BREP objects, and other surface meshes. Here's an example. that illustrates how extraction may happen from faces extracted from these target meshes within specific distance from this source mesh. We also added two tools to extract by area and by aspect ratio. By area extracts faces that fall within minimum and maximum limits of area that's specified by user, and by aspect ratio extracts mesh faces with edge length ratio above the user set value. These two functionalities are somewhat similar to what Rhino offers for meshes. However, they are more robust and they work on multiple meshes. So they just provide a bit more powerful functionality. We also did some significant speed up, which is due to multi-threading and optimizations of algorithms. So you may notice that on multiple meshes, JExtract functionalities work much faster than before. Well, with this, let me switch to Rhino and show you one quick example about JExtract. All right, here's a quick example about JExtract. I'm going to show only use of one functionality within distance. And this example contains number of surface meshes. They represent geological features. For example, this type of meshes and all others, multiple meshes, represent geological layers or boundaries of these layers. And these vertical meshes represent some geological faults. And quite often engineers would like to separate interactions between different types of objects in their model or different types of meshes. And this can be achieved by pretty much separating faces that located nearby these objects. For example, we can just remove faces of geological layers located near the faults. And this can be achieved with command JExtract, extract within distance. First, we need to select source objects. It's going to be our faults. Then we need to select target meshes. It's going to be the meshes from which we want to extract faces. We need to provide some distance within which we would like to extract faces. And this option specifies how to look for extracted faces. So you can read about this option in help or documentation. And let's just press enter right now. JExtract works pretty fast. And you can see that we extracted rows of faces and all these faces are located near the faults. Now we can delete or hide them, and all these faces were placed into separate layers, just in case we want to do something later with them. And we, for example, can hide them for now. So this functionality or this example illustrates how you can quickly and easily use JExtract to do additional operations with your meshes and separate meshes based on different criteria. Let's get back to the presentation and review a couple of remaining functionalities or improvements in the functionalities. We'll start with JExtend. These tools for extending surface meshes. And here we added extend to mesh functionality. It's a new tool that extends one mesh to another along selected boundary while making the connections conformal. Here's an example of how the tool works. Let's say we have target mesh and base mesh, and we would like to extend the target mesh along this highlighted boundary towards the base mesh. This image shows how the extension is created. We can see that the extension is coming from the bottom boundary of target mesh until it intersects the base mesh, and the intersection is made conformal. And the intersected faces are highlighted in red, so in this case it's all the extended faces. One thing to notice that when extending one mesh to another, the extended boundary has to be sufficiently smooth, as well as the base mesh should not have some big ridges or severe kinks or faults. Otherwise, extension may not succeed or be very bad. So we have several options in extend to mesh functionality. The first one is set the extension direction, which can be average tangent along vector normal to base mesh. The first two are actually same as in other JExtend tools. And the last one is kind of new option. And normal to base mesh direction allows extending mesh in the direction perpendicular in local sense to base mesh faces. And this can be very useful sometimes, especially when the target mesh is oriented under very small angle towards to base mesh, or they say nearly coplanar, and we want to create extension of target mesh in such a way that it doesn't produce very thin wedges or tetrahedrons or pyramids when creating volume mesh afterwards. So normal to base mesh would allow creating much better quality elements in such situations. As I mentioned before, intersections, the extension can be automatically intersected and trimmed, and mesh intersection logic searches for most optimal intersection tolerance between the extended part of the target mesh and the base mesh in such a way that this tolerance would provide a single connected intersection polyline. For example, here we can see it would be a single intersection polyline. In some cases, this unfortunately is not possible, especially when working with rather complex meshes, or if target mesh already intersects base meshes, especially in multiple places. In this case, automatic intersection logic may fail. However, users can still extend target mesh towards base mesh without intersecting automatically. In this situation, use of geint will be necessary afterwards, and with geint there are more controls of how to do intersections and visualization, so users will have more options and see how the intersections will work. So this basically outlines how gextend operates. It also automatically checks for various issues and inputs. So hopefully this option will provide more tools for mesh extensions and make it easier to create conformal intersections. The next tool I'd like to describe is gextrude. It's a tool that provides conformal surface mesh extrusions towards, let's say, planes or other surfaces. Here's an example of how extrusion can work. And the tool is designed to quickly create model domains from the surface meshes. And the main improvement here is that we allow extrusions now for meshes that contain multiple boundaries, for example, internal boundaries or holes. Previously, it was not possible, and gextrude would just throw an error. But now, basically, users can pick if they would like to extend only the exterior boundary. For example, in this case of the green mesh, only exterior boundary is extended towards gray plane, or extend along all boundaries that surface mesh has. And here's an example of this. This purple mesh has two boundaries here, the interior and exterior, and it can be extruded, let's say, to another plane, in this case, this brown plane, to create another closed volume domain. So in this way, people can easily create closed volume domains, including nested closed volume domains as shown here, and hopefully this option will make it easier to create domains for volume meshing. Lastly, I would like to mention about Block Ranger. It's our heritage structured hexahedral mesher. We made just a few improvements here. We allowed specifying zone and phase group slots for flag-free and free deck. We allowed we added VTK output for Block Ranger, and we did multiple bug fixes. Here we list general improvements. First of all, it's the ability to turn off non-critical notifications pretty much in all Griddle tools. This can be done through show warnings options. And this is very useful when calling Griddle commands or tools through Python scripting, because people wouldn't want to see pop-up dialogues warning about something that's not critical. So those notifications can be turned off, so Python script can work automatically. We also revised and improved embedded documentation, which can be accessed through Rhino's help panel or via default browser. You just need to press F1 to launch default browser with documentation. We updated security logic, Now it allows 2 seats per 1 web license, and it's the same logic as used in ITASCA software version 9, so many people should be familiar with it already. And we also updated user manual and tutorial examples and added one new comprehensive example, which describes operations with rather complex geometry, very realistic geometry, and use of new Griddle tools. And one final thing I would like to mention is that Griddle will be switching to point releases, same as many other ITASCA software. Point releases will provide maybe smaller improvements in functionalities or a smaller number of new functionalities, but much more frequent than major releases. So users may expect another smaller Griddle release sometime soon. And these point releases will be available through subscription. With this, I would like to conclude the presentation. Hopefully it was informative for everybody. Thank you for your attention.